thank you very much for the kind introduction. And so this is going to be another talk on silicon photonics. I think the stage has been set nicely by the previous talk. Still, I'm going to focus a bit more on the fundamentals rather than on very many details. Okay, so in terms of motivation, we've already seen such charts before. One thing I would like to highlight here, since about 20 years, the number of cores on chips starts increasing very significantly because we don't know what else to do with all the transistors we have available. So we are in the many-core and multi-core era, and the interconnect wall is starting to hit us. The power consumed by moving data around is getting ever more significant compared to the power we spend actually processing data. And electrical networks on chip are reaching their limits. Optical interconnect is a potential solution which can be faster, which can be lower power compared to traditional electric. And a specific technology is a so-called RONOX, wavelength routed optical networks on chips. This is a technology where the wavelengths decides the path the signal takes. I'll show this in a moment. And so actually the key decisions are taken during design time. There is no routing during the execution, so there won't be any contention, for example. And that creates interesting new EDA challenges. So in terms of the fundamentals, the high bandwidth is achieved, for example, by the use of wavelength division multiplexing technology. The key structure is as follows. We have core 1 here, we have core 2, they want to talk to each other, and they do this. This is obviously an electrical signal progressing through electrical wire. Then there is a transmitter here where a laser source is modulated. Then we have an optical signal progressing along waveguides, sent into an optical router where it's then routed to its destination. And then there's a receiver which demodulates the optical signal, converts it into electrical again, and then it goes to the second core. So that's the fundamental idea. We use optical interconnect and optical router to communicate between cores. And the fundamental component is a so-called photonic switching element. We have here two so-called microring resonators. These are waveguides which are turned into a circle, and they are resonant. So when I have light coming in here, it's input 1 on a certain wavelength, which is in resonance with this microring resonator, then that light signal gets deflected by 90 degrees. In this case, you can also have 180 degrees or 270 degrees deflection. So if I then have another wavelength, lambda n, which is not on resonance with these microring resonators, those go straight through the signal. And this is how we affect the routing in a photonic system. So for example, this is a so-called 8 by 8 because we have 8 initiators and 8 targets, lambda router. And you see all these photonic switching elements, about 25 or so of them here in the center. And this is resonant to lambda 1, this is resonant to lambda 2. So each one is resonant to a certain wavelength. And when I then start a signal here at initiator 1, which is on resonance with lambda 4, it goes straight, and then it gets deflected here because this one is in resonance with lambda 4, and so that determines that this signal will go from initiator 1 to target 1. If I then use another wavelength, for example lambda 5, it would get deflected here, so it goes to target 2. So this is basically how we use the optical signals and the photonic switching elements to direct the light. We got started on this research actually about 15 years ago when Davide Bertozzi from Ferrara at the time, he works on architectures for photonics. He came to us and said, well, the manual design we're doing doesn't really go optimal. Can we try to apply EDA technologies for that? And that looked like a very interesting problem, so we got started on this. And there's actually a lot of ISPD in the history, as you can see here. We had our first publication at ICCAT, but then already in 2013, we had a bit of work here at ISPD. We introduced the Platon, our force-directed placement approach at ISPD 2016. Then concept of template-based design 2019, and here 2026 I'm back. And we broadened, we initially started on the physical design, and this has been broadened. We now look at trying to consider topology, so the netlist for RONOX, the architecture, co-design among physical design and topological design, looking at robustness issues, considering crosstalk, and so on. And what I promised in the title is optimality versus complexity. So when I look at the design, I have the topological design where I decide the netlist for my router, and then I have the physical design where I actually place and route it. In the topological design, I define the logical connectivity among all the cores. I do the assignment of wavelengths to the signal paths. And in physical design, then I map the logical connections onto the layout plane and I do the routing. And traditionally, this is done separately. Separation of concerns, because it allows me to deal with the complexity. But that has some drawbacks, as I'll try to explain. So what I'm trying to balance is, of course, I want to achieve as optimal as possible a result, which means the performance factors, resource usage, how many waveguides, how many microring resonators, especially the power consumption that is required, and also crosstalk. How can I optimize this, but at the same time use a reasonable amount of computational time? That's the trade-off we're juggling. And traditional approach is, as I said, separation of concerns. First we do the topological design, sequentially followed by the physical design. The advantage of this is the design complexity can be managed. The disadvantage is that, well, the topological design does not know about physical design, so it may make decisions which are then not very suitable for the physical design. And on the other hand, the physical design simply has to take what is the result of the topological design. And here you can see is this little animation a little bit, this very nice structure. When I do then the actual physical design, it gets distributed all over the place. So that leads to some suboptimality. The second approach is what we call the template-based approach, where we assume that these optical switching, photonic switching elements, that they have a certain structure, and there's fixed locations where microring resonators could be, there's fixed locations where routing can be, and then we just decide which of these predefined placeholders we actually use. So we restrict the design space in a different way. I like to think of this as like going from transistor level design to a standard cell design, where you obviously restrict the design space, but then you can handle larger designs. This gave significantly better results, but only for reasonably small examples. Still, when you go from an 8x8 to a 16x16 or then 30 by 32 by 32 router, the design complexity increases again very significantly. So we came up with two different approaches, which I would like to very briefly introduce here, which try to bridge the gap between topological design and physical design. The first is actually fairly simple. If you recall what I showed here before, so previously, the assumption had been in the topological design, the initiators where the signals originate are on the left-hand side, the targets where they end up are on the right-hand side. Of course, in reality, this is very often not the case. This is memory controllers, this is hubs to cores. They are not nicely on the left-hand side, on the right-hand side. They are distributed over the design plane. And also, most components are both initiators and targets, and they, of course, are at the same place. So we considered this, came up with the fundamental structure, which we call hash, basic building block, where the initiator and input and output, we call that here, for certain core are closely together here, here, here. Build them into a larger structure, which then is projected onto the layout plane. So the structure of the topology of the netlist is actually maintained when we go into the physical design. That's the key idea here. And this is the result of this topology projection, which is, this is the insertion loss, which is a measure for the optical power that we need in the system. And obviously, as in all these results slides, it's better than previous approaches by about 50% on average compared to the traditional previous approaches. The second concept, again, tries to bridge topology and physical design. Here the idea was to come up with a library of different routing components, 3x3 router, 4x4, 5x5, and so on, and to use a mesh-based structure. And then for every, the circles here are the computational cores and the squares are the routers. And so for example, if this core wants to talk to this one, this would be the signal path here. And then for every router, we determine using ILP what is the most suitable of these potential routers from the library, which reduces the resource, the required resources, and what is the most suitable signal path. That's done by an ILP. And as a result, when we compare this to previous approaches, here you're seeing the number of wavelengths we require. This is our previous Psion. This is from Yao and Chan, the co-design methodology. This is ours. That's pretty much identical. We need one additional wavelength. The bars here, this is the power consumption. And you see that this new approach has a lower power consumption. And this is primarily driven by this part up here, which is the MR microring resonator thermal tuning power. You can see here we use much fewer microring resonators because we also make use of the fact that they are the microring resonators, they are resonant to different multiple wavelengths. And since we have fewer of these MRRs, we need less tuning power, which then reduces all the power consumption. And the technique is very fast. I mentioned before, Psion can take a very long time for larger approaches. I hope that I have managed to give you a little bit of an idea of what the fundamental challenges in using optical networks on chip are, and two recent approaches how to address them by being layout aware in the topological design, and then being interconnect preserving in the physical design, and then secondly a co-optimization framework which utilizes the mesh structure and efficient optical routers. And with that, I guess I'm over time. Thanks a lot for your attention.
Thank you so much, Rolf. Do we have any questions from the audience?
I think Lou's voice is pretty loud in any case, right?
Yeah. Well, thanks very much for the talk. And my question was simple. Why does it take power to tune the optical resonators? Aren't they determined by the physical dimensions?
Yeah, that's correct. But they are also fairly sensitive, for example, to temperature. So that's one reason why you want to tune them, depending on the specific circumstances under which your chip is operating. And there's manufacturing variations, just like in traditional electronics.
But that would mean you can't cool them, so you have to run all of them at the highest possible temperature you're ever going to reach. Is that the case?
Sorry, say again?
Oh, you can't cool them, you can only heat them.
Yes.
Yeah.
Yes.
So that would mean you have to pick a high temperature in case your outside temperature is too high, then you're stuck. So you'd have to, it seems like you would have to heat them to a high temperature to tune them.
Well, hopefully I cannot cool them, you're absolutely right. I can only heat them, but I do not necessarily need to heat all of them. It's not like, I'm not the technology expert, but it's not like you would go from 25 or let's say 25 degrees centigrade to 125 or so. It's a minor tuning in my understanding.
Thank you.
I think we have time for one more question.
I have one question. So do you have already any example implementation of this kind of architecture you're just suggesting here? Do you have really chips already produced?
Manufactured chips?
Yeah, manufactured chips?
No, we're EDA guys, but some of the groups, for example, Daniel Bertozzi that I mentioned, he is actually using some of our tools. So there have been chips designed, with not with the most recent stuff I was explaining here today, but with some of our older tools. They have been used by groups that actually design these photonic chips, but we're the EDA guys.
All right, let's thank the speaker one more time.